Hello everyone, this is GEETHA from CSE department. In this lecture, we will be discussing about representation of graph. Graph is a nonlinear data structure which consists of vertices and edges. So now we are going to represent the graph. As it is, graph will be represented in diagrammatical representation using vertices and edges. But if you want to store the data of graph in the memory, you're going to have certain order for it, or you're going to have certain representation for it. So to represent the graph, we will be using two types here. The first one will be adjacency matrix. The other one is the adjacency list. So first we'll cover about adjacency matrix. Here you're going to represent the graph in a matrix way. That is, in a 2D array, you're going to represent the graph. So you can see this example here. For this case, we are considering the undirected graph representation. So here this is the graph, and this is how you are going to represent the graph for storage purpose. So you will be writing all the vertices present in the graph in a horizontal and vertical way, and you are going to fill out the matrix now. So A to A. So if you A and A. So this means that A to A, if there is any connection, you are going to give it as 1. But here A to A, that is self edge is not present here. So A to A, it is 0. And then A to B, you are going to check whether A to B the connection is there or not. So yes, A to B the edge is there. So A to B, it is 1. Then A to C also edge is present, so 1. Then A to D, edge is present, so 1. But A to E, there is no direct connection. Here you are going to just consider about whether the edge is present between two vertices or not. But considering the vertices A and E, there is no a single edge connection from A to E, so it is represented as 0. So similarly, we'll see another one example using the vertex D. So now, we'll see with E. So E to A, if there is any connection, E to A, there is no direct connection, so it is 0. Then E to B. E to B, there is a single edge connection, so it is 1. And then E to C also there is no direct connection, so it is 0. Then E to D, there is a direct connection, so it is 1. And E to E, there is no self edge, so it is 0. And considering this self loop, we'll be calling it as a loop here. So D to D, there is a self edge or loop here, so D to D, it will be represented as 1. So this is how we'll be representing in a 2D array for undirected graph. The next we'll see for directed graph. Here there will be a certain direction will be given for the traveling purpose. So here you can see you can travel from A to B but cannot travel from B to A. But if it is undirected graph, considering A to B, you can also travel from A to B as well as B to A you can travel, but that is not possible using directed graph. So we'll see the matrix here. So A to A, no self edge, so it is 0. A to B, yes, there is a edge pointing from A to B, so it is 1. B to C, is there, A to C also there is a directed edge, so it is 1. A to D, so there is no edge present between A to D. You cannot travel directly from A to D. It is possible to you to travel from D to A, but it is not possible vice versa. So A to D, it is 0. And also considering A to E, there is no direct edge first of all, so it is 0. We'll consider another one example with D. We'll go with D. So D to A. D to A is D to A, there is a pointed edge towards A, so you can travel from D to A, so 1. D to B. D to B, it is not possible, so it is 0. But you can travel from B to D. Then next one, D to C. D to C also you cannot travel because it is in a reverse position, so it is D to C is 0. And D to D, there is a self loop, there is a self edge or loop present in D. So D to D, it is possible to travel in a single edge, so it is 1. Finally, D to E, yes, from D and edge going points towards E, so it is 1. So this is how you will be representing the directed graph in a 2D matrix. The next one is weighted graph. So we know if in the previously we saw about unweighted graph, there is just directed or undirected, but the next phase is about weighted graph. Each edge will be having its own cost or weight. So here we'll be first addressing the undirected weighted graph. So edges are undirected here, but all the edges are having weight. So this is undirected weighted graph. So A to B, similarly same matrix format. A to A, no loop here, so 0. Next one A to B. A to B, yes, the connection is there, but you should not represent 1 here. Instead, you will be representing the how much the weight between A to B. So A to B, you are going to represent it as 7. The cost or weight represented in the graph as it is, you are going to write here. The next one A to C. A to C, yes, you can travel using the cost of 8. So A to C, you are going to represent it as 8. The next one A to D. A to D, there is a straight connection to A to D with the cost of 5. So A to D, you are going to represent it as 5. The last one A to E, there is no direct connection from A to E, so it is 0. So instead of representing it as zeros and ones, you are going to represent using the weight that has been allotted for each edges. So this is how undirected weighted graph will be represented. The next one is directed weighted graph. Previously we saw undirected. Here the thing is just a directed one. So here you can see all the edges are directed and also it has its own weight. Similarly, instead of using alphabets, here they went with numerical vertices. That is the difference here. So you write all the vertices 1 to 5 and 1 to 5, and then you're going to do the matrix now. So 1 to 1, no loop here, no direct edge, so it is 0. 1 to 2, you cannot travel from 1 to 2 directly, so it is 0. The next one 1 to 3. 1 to 3, yes, direct edge is present there with the cost of 6. So 1 to 3, you're going to represent it as 6. The next one 1 to 4. 1 to 4, yes, direct edge is present with the cost of 3. So you're representing it as 3. The last one 1 to 5. There is no direct edge from 1 to 5. So you're representing it as 0. We will see another one example using 5, vertex 5. So 5 to 1, no direct edge, so 0. 5 to 2, yes, one direct edge is there. So with the cost of 4, you're going to represent the cost 4. 5 to 3, no direct edge, so it is 0. 5 to 4, yes, direct edge is present with the cost of 2, so represent 2. 5 to 5, no self loop, so it is 0. So by using this is the 4 types of representing graph in array format or in adjacency matrix format. The next type or next representation format is adjacency list. So here instead of representing the graph in array, you're going to represent using the linked list format. So you see the example here. This is the directed graph. Now you're going to form a header format. We know a header will be there. From the header the linked list starts. So whatever the edge is present, each one will be connected in the linked list. So similarly, by using that representation, you are going to represent the graph here. So whatever the vertices are there, you order all the vertices here as a header, and then the linked list starts. So from the A vertex, which are all the vertex can be traveled directly. You can travel from A to B and A to C, and you cannot travel for any other nodes except B and C. So A has been connected to B, so you form a node there, connect A and B, and then the next edge, next vertex you can travel is C. So from B, draw another one connection and draw the node for C. So only BC can be traveled from A. So C is the last node. So the next of C will be null. So that's why they crossed the next part there. The next vertex is B. From B you can directly travel from D alone. D as well as E. Two vertex can be traveled from B. So from B, D has been connected as well as E has been connected. After E, no edges are there. So the next part will be null for E. The next vertex is C. From C, you can directly go to D alone. So C will be connected to D. The next one, D vertex. D vertex is having self edge as well as it can go for A as well as it can go for E. So 3 vertex can be visited from D directly. That is A, D, E. So from D, A has been connected and then D and then E. From E, no direct connection is present for any vertices. So as it is, the header next of header will be null. So this is how adjacency list representation will be there using the linked list format. The next one, the same adjacency list representation, but it is used representation for weighted graph. So here as it is, you wrote the what are the vertices are connected. Here you are going to consider the weight also. So you represent all the vertex present in the graph 1 to 5 we represented here as a header, and then you check from 1 which vertex you can travel. So from 1 you can travel to vertex 3 as well as 4. So now along with the vertex name you are going to consider the weights also. So from 1 you can go for 3 node 3 with the weight of 6. So only that's why it is represented as 3 and 6. The next one is from 1 you can travel for 4. So it is 4 with the weight of 3. So 4 and 3 has been represented. By considering the vertex 2, from vertex 2 you can travel only to vertex 1. So vertex 1 with a cost of 3. So each edge is having a cost for it. So you can represent the cost here. The next one is vertex 3. From vertex 3 you can travel directly to 4. So vertex 4 you can travel with the cost of 2. Similarly for vertex 4 you can go for 3 as well as 2. So 2 with the weight of 1. You can see here 4 to 2 with the weight of 1. So 2 1 1. The next vertex is 4 to 3 with a weight of 1. Finally vertex 5. From vertex 5 you can go to 2 as well as 4. So from 5 to vertex 2 with the cost of 4, and from vertex 5 to 4 with the cost of 2. So 5 to 4 with the cost of 2. So these are the ways of representing graph for storing it in the memory. Thank you.